Good afternoon, everyone. As you know, your test on trig is tomorrow. Today we need to move on to the first lesson of our next unit because we're running out of days to get things done. So today we're looking at unit number 4, exponential and logarithmic functions. We're just going to be focusing on exponential functions today. You did look at some exponential functions in grade 11, so most of the stuff today should be mostly review or a refresher on what was done in grade 11. So the first example, number 1 here, we're asked to graph the functions y is equal to 2 to the power of x. We're going to do that one in red. And y equal to 1/2 to the power of x. We're going to do that one in blue. Once we've graphed them, it asks us to state the domain, range, and end behaviors of each function. So as you can see, we're going to be using a table of values for our graph here to give us a general idea of what the shape is. And we're going to use our x values from -2 to 2. So let's plug in each of our x values to get our y values. 2 to the power of -2 is 0.25. 2 to the power of -1 is 0.5. 2 to the power of 0 gives us a value of 1. 2 to the power of 1 is 2. And 2 to the power of 2 is 4. Oops. Okay, and then let's do the same thing for our blue graph. So 1/2 to the power of -2 is 4. 1/2 to the power of -1 is 2. 1/2 to the power of 0 is 1. 1/2 to the power of 1 is just 1/2, but because we're doing a graph, we're going to put that in decimals, so 0.5. And 1/2 to the power of 2, again, is a decimal, and it's 0.25. Now that we have each of our table of values, let's go to our graph and plot our different points. Now that we have our points, draw your nice smooth curves. Put your labels on them. So now that we have our graphs, let's go through and state the domain, range, and behaviors. Oh, one other thing that we might want to talk about is where our graphs reach our x-axis there. Now, the thing that we want to look at is, do our graphs ever cross that x-axis? If you remember anything from last year about exponentials, base exponentials like this without any transformations will never cross that x-axis. There is no x-intercepts. And we have, because of that, we have, if I can get the marker to work here, our asymptote that y cannot equal 0. And that's one of the key features of exponential functions, is that when there's no transformations, that they have that asymptote at y cannot equal 0. So let's quickly go through and pull out our domain and range. So for our domain, for our red graph, y is equal to 2 to the power of x. We look at if there's any restrictions on our x value. Because it goes in both directions and continues on forever, there is no restriction on x, so x is in the reals. Or if we're using our interval notation, which we learned this year, we would say that x is between negative infinity and infinity. Or, okay, then we have our range. We have our range. For our range, we're looking at the restrictions on y, so we see that the x value, or sorry, the y value, it's always greater than 0 because of the asymptote, never crosses. So we can say that y must be greater than 0, and y is in the reals. Again, or if we were doing our interval notation, we would have to say it's between 0 and positive infinity. And we put a round bracket around the 0 because it never actually hits the 0, it just gets really close to it. But because it doesn't actually hit that point at 0, we need to put the round bracket. And our last piece is then our end behaviors for our red graph. Remember, with our end behaviors, we state as x goes to positive infinity, and then state what happens to y. So as x goes to positive infinity, then y approaches what value. So look at our red graph. As x gets exponentially big, it's getting really, really big, it's going to positive infinity. Our y value is going up, and it's also approaching positive infinity. And then we also have to consider as x goes to negative infinity, what does y approach? So we look as x gets bigger in the negative section and goes to negative infinity, it's approaching our asymptote at 0, so we're saying that y approaches 0. Let's then take a look at the domain and range for our blue graph. So for our domain, again, x continues in both directions forever. So we say that x is in the reals, or you can say that x is from negative infinity to positive infinity. For our range, again, it's the same thing as our red graph, where it can go up in any direction, but it only will ever approach that asymptote, so y has to be greater than 0. Y is in the reals. Again, or we could use from 0 up to positive infinity in our interval notation. And then again, we need to look at our end behaviors. For short form, we can just call that AB. So we have to consider as x goes to, as x approaches positive infinity, then y approaches, so as x goes to positive infinity, y is then approaching our asymptote at that end there, so y is approaching 0. And as x goes to negative infinity, then y approaches, so again, we look at our blue graph, as x gets really big in the negatives, y is going up, so y is approaching positive infinity. These key things for domain and range and end behaviors, the shape and property of these two graphs generalize all the exponential functions in terms of the general form of exponentials. One other thing that you should have hopefully noticed is that the only difference between these two graphs was that they were flipped in the opposite direction. Our red graph, it was an increasing graph. Oops, let's do that in red. Our red graph was an increasing graph. Because when we read our graphs from left to right, it increases, it goes up. Our blue graph, it was a decreasing graph. Because as we read our graph from left to right, it decreases, it falls down. That was the only difference between those two. They had the exact same values, they were just flipped in those opposite directions for one to be increasing and one to be decreasing. At this point in time, if there's still people who are still writing, pause the video. I'm going to move on to the next slide. So we're going to just look at our definition of a basic exponential function. And again, most of this should be review. So the basic exponential function, we have that f of x is equal to b to the power of x. Now there's a couple different conditions depending on what the value for b is, and we saw this a little bit in that previous example, where if our base, the b, is greater than 1, then our function f of x, it increases from left to right. I need just more space in there. So our graph increases from left to right when our base is greater than 1. If our base is a fraction or a decimal value, so it's in between 0 and 1, then our f of x decreases from left to right. And with graphs, remember, we always read the graphs from left to right. Another key piece of basic exponential functions is their y-intercept. They always have the same y-intercept, and it was true of our two graphs in that first example, is y-intercept is always the point 0, 1. The only time that changes is if we do transformations to shift it around the graph, but otherwise when it's the basic exponential functions, we always have that intercept, because any number to the power of 0 is always the value of 1. The last key piece of all of our exponential functions is our horizontal asymptote, that y cannot equal 0. We're also going to look at other pieces of exponential functions. This may be something new. So we're going to consider our table of values that is shown here. And we need to figure out, is this function exponential? Now, when we look at a table of values for other functions, we're able to identify polynomial functions by their finite differences. And we did that in the first unit with our polynomials. But the question we want to ask ourselves is, can we do the same thing with exponential functions? Does something with a table of values be able to tell us something about the exponential functions? So let's go through and come up with our first and second differences and see what they might tell us about, our function here. So let's do our first differences. So remember, with our first differences, we usually start from the bottom and work our way up, subtracting out. So we would do 625 minus 125, which gives us a value of 500. And again, we go one up, so 125 minus 25, which gives us a value of 100. And keep going, 25 minus 5, that's going to give us a value of 20. And 5 minus 1, that's going to give us a value of 4. Remember, we don't do this one here because there's nothing above the 1 to subtract out. That's just an NA, or you can shade in the box in your table of values. So looking at our first differences, We have a 4, a 20, a 100, and a 500. That doesn't tell us anything except that we know that it's for sure not linear. Because remember, first differences, if they're the same, it's linear. If they're not the same, then we know it's not linear. Let's take a look at our second differences. Remember, with the second differences, we're doing the exact same steps, except now we're doing them with the values of the first difference. So we're taking 500 and minusing out 100. So we get 400. We're going to do that again. 100 minus 20. That's going to give us 80. And 20 minus 4. That gives us 16. We can't put anything in these two blocks here because, again, there's nothing above that 4, so we don't have any values to subtract out. So we can just box that out. So looking at that second difference again, there doesn't seem to be any consistent pattern from 1680 to 400. There's no obvious pattern there. They're not all the same. If they were all the same, that would tell us it would be quadratic. So that doesn't help us out overly much. There's one other thing that we can consider that might help us out is first and second differences. That was dealing with subtracting out. What happens if we look at the ratios of those numbers? So instead of subtracting, let's actually divide. So if we take 625 and divide it by the 125, we get a value of 5. And if we do that again, but with the next line, so 125 divided by 25, we get a value, again, of 5. Well, this is starting to look promising. So keep going. 25 divided by 5 gives us 5. And 5 divided by 1 also gives us 5. So we notice here that all of our ratios are in fact the same. One other way that you might have noticed this, if we just look at our original y values, is we find that our successive values, so the ones below it, we get it by multiplying by 5. 1 times 5 is 5, 5 times 5 is 25, 25 times 5 is 125, and 125 times 5 is 625. If you notice that pattern, that's the same idea as our ratios to figure out what that pattern is. So what that tells us is that in a table of values, if we're given a table of values and we calculate the ratios, if all of those ratios are the same, we have a constant ratio, then that means that it is an exponential function. Not sure if I have that written on the next page. Nope. Okay, so let's add that into our notes here. So if a function is exponential, then its table of values will have a constant ratio. And that means the ratio that we calculated is all the same. Now the other thing that tells us in more proper notation wording is that our rate of change is increasing proportional to our function. Remember, rate of change is in relation to slope, but it's changing in the same amount that our function is changing in. the last little piece here is, what is the equation of the function and how can we figure that out? One nice thing about exponential functions and the table of values with figuring out the ratios is that our equation comes directly from that table of values piece. So because our constant ratio was a value of 5, that means its rate of change, as we just talked about, was changing by that value of 5, being multiplied by 5 every time. So what that means is the ratio that we figured out, that's the base of our function. So because the constant ratio is the base of our exponential function, that means our function is f of x is equal to 5 to the power of x. So if you're given a table of values, you should be able to figure out if it's exponential based on calculating the ratio, and if they're all the same or not. And if it is an exponential function, you should be able to come up with the equation, which is just the base to the power of x. And the base comes from the constant ratio. Another thing that we're going to look at with exponential functions is exponential models. So this is dealing with some word problems and applying exponentials to real life. Our general formula for exponential models is y is equal to c all multiplied by a to the power of x, where a is our growth or decay factor. So when we're talking about exponentials in terms of word problems, we use the word growth and decay instead of increasing and decreasing. And then the c, that is the new part of the equation, that's the initial value. So that's the value it started at to begin with before it either started growing or before it started decaying. So just like with our general form of our exponential equation, with exponential models, we can tell if it's growth or decay based on our base value. So this is exponential growth if our a value is greater than 1. And we can tell if it's exponential decay if our a value is in between 0 and 1, meaning it's a fraction or a decimal. So it's the same rule that was with our general one, it's just a slightly different equation because it has that initial value. A couple different examples of where exponential relations actually occur in real life. A lot of them occur in science, as well as population growth and radioactive decay, and specifically as well in finance with compound interest. And you would have seen that last year in grade 11 as well. So we're going to take a look at an example of using this exponential model. So we're looking at the number of certain bacteria, and it tells us that it doubles every hour. The initial population in a culture of this bacteria is 36, and it asks us to determine an exponential model for the number of bacteria after t hours, and then determine the number of bacteria after 8 hours. So the first thing is when it tells us to determine an exponential model, that means it wants us to come up with an equation. So whenever it asks you for an exponential model, that's just coming up with a base equation that has the two variables with some other numbers in it. And then it asks us to figure out a value for that number of bacteria after a certain amount of hours, which in this case is 8. If you want a minute or so to copy this down before we go through the example, just ask to pause the video at this point. So let's take a look at what information they've given us. They tell us that the initial value of the bacteria is 36. So we know our initial value of our bacteria is 36. It also tells us about the growth factor. At the beginning, it says the number of certain bacteria doubles every hour. So that's our growth factor. Because it doubles every hour, that means our growth factor is a factor of 2. And that was because it said it was doubling. So we look at our general form of the exponential models, which is y is equal to, well, I guess we use f of x. F of x equals to c a to the power of x. So plug in the pieces of information. We should have values for the c value and the a value, so we only have our variables left over. So f of x is equal to, our initial value is 36, and our base value a is our doubling, so that's 2 to the power of x. So that's the first part of the question where it asks for our model. So this is our model here, that f of x is equal to 36 multiplied by 2 to the power of x. The next piece asks us to figure out how much bacteria we have after 8 hours. So after 8 hours, we're going to plug in that x is equal to 8, because x is our time factor, because the f of x is the amount of bacteria. So we plug in our value for x. With this, when you're plugging it in, you can just plug this into your calculator all at once. The one warning I will give is you need to make sure that you do 2 to the power of 8 first, and then multiply by the 26. You have to remember your BEDMAS rules, exponents have to be done first before you do multiply. Otherwise, you'll get the wrong answer. And you should get 9,216 bacteria as your answer. At this point in time, if you still need a chance to write it down, pause the video. I'm going to move on to the next slide. We're going to be looking at converting percentages of growth, converting percentages to growth or decay rates. This is important because often in real world situations, we're not just given the information as a growth or decay rate, we're given it in percentages because that's what makes sense to most people. And then we have to convert it into our growth or decay rate to be able to plug it into our exponential model. So the first example we're going to look at is an investment that it increases by 5% a year, and it asks us to figure out what is the growth rate of this investment. So because our investment rate increases by 5% per year, that means 5% increase implies a growth rate of 100 plus that 5, because every single time it grows, it already still has that initial amount that it started with, that 100% that it started with, and then it's getting an additional 5% every single time. So in our equation, it would actually be a 1.05 because we don't use percentages in our actual equations or calculations. So because it's a 5% increase and we have to keep that initial amount every single time, we have to add that 100% of the initial amount that it started with, plus the 5% each time of its growth. So it gives us a total of 105% that it's increasing by. And then we put that into decimals because we can't have percentages. That's 1.05. So our growth rate is 1.05. And that's the one that we would use in our equation if we were asked to plug it into our model or something like that. Your next example, example number 5. It tells us the value of a certain kind of car depreciates by 12% per year. This one asks us, what is the decay rate of the value of this vehicle? So because it's a 12% and it's a decay rate, so that means it's decreasing. So 12% decrease. Because it's decreasing, we know it's a decay rate. Now with this one, when it's decreasing or its decay rate, it tells us how much it's decreasing by, is what we really want from that information is how much is left over after the decrease has been taken away. So because we want how much is left over, we need to do 100%. So again, 100% is just the amount that it starts off with to begin with, minus out our 12%. And that gives us an 88%, which is, again, in decimals, because we can't have percentages in our models, is a 0.88. And again, the reason we have to minus that out is our equation needs to find how much is left over after that decrease has been taken away from our initial amount. So our actual decay rate that we need to include in our equation is the 0.88, because that is what's left over after it's decayed by 12%. Our last example talks about what is the average annual rate of inflation of a loaf of bread that cost $1.19 in 1991 and $1.50 in 2001. In this case, whenever we're given certain amount of years, so from 1991 up to 2001, we need to include what is our baseline, so what is our starting point. And so we're going to let the 1991 value be our baseline. And we need to include that because in some cases, especially with inflation, sometimes you're told what your baseline must be. So in this case, we need to state that we're letting our baseline be our 1991 year. For this one, we actually have to plug it into our equation because we're given two different values. We need to figure out what it is. We can't just pull it out just like we did with the other ones. It's giving us the other pieces of information in the equation. So we look at our general equation for exponential models and think about what information we've been given. So because our baseline is 1991, it means that $1.19 is our starting value. So that means our initial value of C is our 1.19, because that's the amount that we're starting off with. It's our initial value for our cost of a loaf of bread. The 150 in 2001, that is our current value of the cost of a loaf of bread, because we're looking at 2001, which is where we're ending off. So that's the current value in that point, which is our Y value. So we put 150 for Y. Y is what we currently have left in terms of our equation, or what's left over after our decay or our growth. For our A value, that's what we're trying to figure out, because we're trying to figure out what is our rate. How much is it changing by between 1991 and 2001? So that's the variable that we're trying to solve for. And our last piece is the x. X is always our time. So in this case, we're looking at how much time has passed between 1991 and 2001. That's 10 years that has passed, so we throw in that x is equal to 10. Now that we've put everything into our equation, our last step here is now just to rearrange it and be able to solve for our a value. So our first step is going to be to divide out this 1.19 from in front of that a value. So that 150 divided by 119 is equal to a to the power of 10. And then we need to get that exponent up to the power of 10 off. So just like if it was an a squared, we would square root. In this case, because it's a to the power of 10, we would do a 10th root. So remember, different types of roots, when it's a 10th root, that's when the number is sitting in the little spot inside the root symbol, and that's just a special button on your calculator. Typically it looks like a little star and then the square root symbol. And that gets a by itself because the 10th root cancels out our a to the power of 10. And then hopefully you found that button on your calculator. You should just be able to plug it in so that a is equal to so our a value is equal to a 1.023. So our rate is 1.023, but we want to put that in terms of percentages for our final answer because that's what makes sense to most people, because seeing a rate of 1.23 won't make sense to them. So we want to put that into percentages. So remember, just like when we started off with it increasing by 5%, we had to add 100 and then turn it into a decimal. We're basically going to do that backwards. So if we multiplied this by 100, to put it into percentages, that would be 102.3%. And then if we minus out that 100 that we had to add in to begin with, in terms of going backwards here, then we would get 2.3%. So therefore, our rate of increase for our loaf of bread is 2.3% after those 10 years. So at this point, this is all the examples that I have to go through. If you have any questions about this, make sure that you are coming in for lunch to ask any questions about this. Tomorrow, your trigonometry test is going to be during the lesson, so if you have any questions about that, again, you can come in at lunch as well. So please make sure you're going through all those different problems and you're practicing those identities, and please make sure you have those special triangles memorized because those are really important for tomorrow. So these are some homework questions that are related to the exponential functions and exponential models that we looked at today. Even though I know you're going to be studying for your test, please try and look at some of them, or if you don't get to them tonight, make sure you look at them tomorrow so that you've practiced some of this as well. Hope you guys have a great day, and I will see you tomorrow.